Today we study X18NQ, the simple and damped harmonic oscillations. If you have no problem with studying X18Q, you don't have to study this. And you can find the lecture file of this from KPOPE.org. Visit there, kpop.org. You will find X series first, and there is X18. If you click X, it is a textbook for X18, and there are Korean lecture, English lecture, today, and X18 checkpoints, X18 checkpoints Korean, and X18 checkpoint English, and this is X18NQ. And after finishing this lecture, I will upload this link here, and the main lecture is X18Q. Okay. Let's start. Solve x squared equals plus 1. Middle school student can solve this problem. And to solve this quadratic equation, you will move this plus 1 to the left-hand side, and it becomes a 0. Because this is factorized, x squared minus a squared equals x plus a times x minus a. Therefore, it is factorized into x plus 1 and x minus 1. If the product of two numbers equals 0, then it is either the first factor is 0 or the second factor is 0. This one will give x equals plus 1, and this one will give x equals minus 1. Therefore, the solution of this quadratic equation, x squared equals 1, is either plus 1 or minus 1. Next, what is I? I is defined by the square root of minus 1. Hence, if you square this, the result is minus 1. Square root of a's square is a. Because square of minus 1 is a plus 1, we find that we have plus I squared and minus I squared. It is plus 1 squared I squared, and this is a minus 1 squared I squared. We know I squared equals 1. So it is 1 times 1 equals 1. Wait, minus 1. 1 times a minus 1 is a minus 1. And this is 1 times minus 1 equals minus 1. So we find that plus I squared equals minus 1, and minus I squared equals also minus 1. Solve the quadratic equation x squared equals minus 1. With the same way, we follow the same way to solve the equation x squared equals plus 1. First, move this one to the left-hand side, that it becomes a plus 1. Now we can factorize this because x squared plus 1 equals x squared minus 1. And we know minus 1 is I squared. We use the factorized form plus I minus I. Therefore, we arrive at the factorized form. The product should be 0. As a result, this one gives the value x equals minus I, and this one gives the value x equals plus I. So, the solution of x squared equals minus 1 is either plus I or minus I. Next, we consider the quadratic equation. This quadratic equation. In mathematics class, you must have learned in such a manner. Squared ax squared bx plus c equals 0. But our objective of this class is to study the harmonic oscillator. So it is better to make use of the parameters that appears in the harmonic oscillator. So you will find it is convenient. Okay, so we want to find the solution of this quadratic equation. Here, m is the real parameter, and actually it originates from mass. But at the moment, let us restrict ourselves to just pure numbers. B comes from the fact that force applied to a particle that is moving accepts a damping force that is opposite to the velocity of that particle. So the opposite means a minus x dot, and B is a positive number. So this is damping force coming from, and this comes from F equals ma. Acceleration of a particle is mass times the force applied to net force applied to a particle of mass m is the net force is mass times acceleration. So m is this one. And the k comes from the fact that we are interested in the restoring force of a spring with the spring constant k. So anyway, all of the three parameters are real and positive. Okay? You'd like to make a transformation by shifting the variable, substituting x with the y minus lambda, where lambda is a constant. We'd like to rewrite, our plan is to rewrite this into a very simple quadratic equation. And this quadratic equation will eventually collapses into either this or this. That is my plan. Okay, so we first assume that this one, after substitution, reproduces the original quadratic equation. If it is not the case, then we have to find another way, but actually, eventually, we will find that it works. Okay, substitute y equals x plus lambda, and lambda is a constant. We substitute x plus lambda for the y in here. Then we have m x plus lambda squared plus kappa. This is lambda, and this is kappa. We expand this x squared to lambda x plus lambda squared, and kappa is there. We rearrange this expression by expanding this mx squared, and linear term is 2 lambda mx, 2 lambda mx. And then constant term, there are two, m lambda squared plus kappa equals 0. Okay, so if I can reproduce this original quadratic equation, I have three constraints. M should be the same. It's fine. It's already satisfied. B should be 2m lambda. Because m is already known, B is dependent upon lambda. Okay, lambda has been determined from this comparison. Once I know the lambda, then I can substitute this one here. This one is determined in terms of mass m and b. And then, what's next? K should be the same as this. So I can determine kappa in terms of m, b, and k. So all set. We are ready to solve the problem. So this is a copy of this expanded form. And this is the original equation. First, it's fine. And we compare this. This one gives a first constraint. And then second, this constant should be the same as k, constant k. Solving this, I can determine lambda to be b divided by 2m. And because kappa is k minus m lambda squared, and I know the lambda, substitute then m lambda squared for m squared. Wait a second, this is lambda, m lambda squared. Okay, so there is mistake. Okay, we determined lambda to be b over 2m, and from this equation I can determine kappa as a linear combination of k and lambda squared, and actually lambda is already determined like this, so I can substitute in here. Then we have a minus m b squared over 4m squared. So cancel. We have b squared over 4f. As a result, we can express the simplified form. Why don't we solve this equation first? Move this one to the right hand side and divide both sides by m because m is non-zero. So y squared is k over m. We remembered x equals y equals x plus lambda. Y equals x plus lambda. So x equals y minus lambda. Therefore, we can make use of the fact, and I just copy this result here. First, we consider the case quadratic equation has a trivial solution y equals 0 if kappa equals 0. So when kappa equals 0, then this equation is y squared equals 0. It is trivial. So the only solution for y is 0. Because y equals 0, x equals minus lambda. And lambda has been determined like this already. So we have the value for x to be minus b over 2m. There is only a single solution. Next, we consider the case when kappa, both m and kappa are positive. If it is the case, because both of them are positive, then y squared is negative. If y squared is negative, solution for y is plus minus I because of this negative sign, and square root of kappa over m. This is positive number. And we have positive number multiplied by plus minus I. Alright, in order for this kappa to be positive, because of this, it is positive. That means k is greater than b over 4m. Alright, in that case, we substitute this kappa, that is k minus b squared over 4m, and we have a denominator m. Okay, so kappa over m equals k over m minus b squared over 4m squared. That is k over m subtracted by b over 2m squared. Aha! This is kappa over m. Okay, so the solution for x is y minus lambda, and lambda equals b over 2m. And then we make use of this result, substitute this value for the y. Finally, when kappa is positive, then k equals greater than b squared over 4m, and that is equivalent to k over m is square of b over 2m. In that case, x is minus lambda, that is minus b over 2m, plus minus square root this one, k over m subtracted by square of b over 2m. Next, we consider the case when kappa is a negative. Everything is the same except that we have opposite direction. This inequality is flipped. As a result, plus minus I is replaced with plus minus. And because kappa is negative, it's better to have a positive value inside the square root. That means this one is positive because kappa is negative. In that case, the order of these two terms are flipped. So we exchange these two. Finally, when kappa is negative, that means this b over 2m squared is greater than k over m. The solution for the quadratic equation is this plus minus square root, a big one subtracted by small one. Okay. So find the power series expansion of exponential x. I believe we know very well. Bernoulli's definition of Euler number is like this. If x equals 0, e to the 0 is just 1. If x equals positive, we take the power and we multiply this law of exponent gives the product of these two powers. And why don't we multiply x over x, because x is non-zero, then 1 over n is shown like that. And why don't we replace this one by n prime? In the limit as n goes to infinity, we doesn't care whether we keep n to be an integer or not. That's fine. So we replace this one by n prime, and we can make use of binomial expansion to find that this one is this. When x is a negative, then it's better to rewrite this one as an inverse reciprocal of this, and in that case we need to replace the power to be minus of x. Because x is negative, and minus x is the absolute value of x that is positive. As a result, I can still make use of the result obtained in here. So this one appears in the denominator. Wait a second. It should be actually they are the same. This is the same as, wait a second. This one should be, I think it should be absolute value, and this should be corrected as x absolute value because I have this. So let me correct this one in the final version of the PDF file, and we redefine this one should also be an absolute value of x, and absolute value of x is replaced with n prime. Then we find this. We can make use of binomial expansion. Newton's generalized binomial expansion can be used to expand this one as a power series. So, and actually this is equivalent to the sum of the geometric series. If we expand this one, we have many more terms, but higher order terms will vanish absolutely according to the binomial expansion, keeping the leading contribution only. In that case, it is explicitly written in the form is a minus x absolute value to the k, this one. And actually x minus x is x absolute value. Therefore, I can replace this one with x to the k. Okay, let me add additional step between them. Number 6. Find the derivative of exponential x. We know the derivative of exponential x. However, let us repeat. Exponential x derivative is by definition, exponential x is replaced with the Bernoulli definition. And why don't we replace this guy with capital X of n? Then this is capital X of n to the nth power. We'd like to take the derivative of this with respect to small x. We make use of chain rule and first take the derivative of this guy in terms of with respect to capital X of n, and multiply the derivative of x of n capital with respect to small x. As a result, we find this one is this, and this one I substitute the original value here. The derivative is trivial, that is 1 over n. And this 1 over n and this n cancels, they cancels, and we are left with this. Finally, we have xn to the n minus 1. That is n minus 1. Why don't we multiply one more piece and divide this one by 1 over n. And limit as in the limit as n goes to infinity, this one is nothing but the Euler number to the x power. So let's see, it should be removed. This one should be removed. All right, so this one limit is this, and in the limit as n goes to infinity, the denominator is collapsed, saves into a unity. As a result, exponential x is obtained. Another way to compute the derivative of exponential x can be made by making use of the power series expansion. We use a power series expansion of the exponential function, and we know how to take the derivative of the polynomial. The sum is over k that runs from 0 to infinity. Therefore, we have the first term at k equals to 0 vanishes. Then the sum starts with k equals to 1. And we can shift back this index. If I substitute k equals to 1, then it becomes a 0 factorial and x to the 0. Aha! So this summation, this sum can be written in this form. What's that? That is identical to the original power series expansion of the exponential function. Next, we consider the derivative of exponential a of x. So, exponential a of x derivative, we can make use of this variable y, changing the variable, and then apply the chain rule. So, this one is exponential y, and apply the chain rule. Take the derivative with respect to y and the derivative of y with respect to x. Now, we obtain dy over dx is a. Okay, so, and then this is identical to e to dy because of this. So, we obtain this. If we repeat the derivative by n times, the result is we have a factor of a by n times. So the final answer is a to the n exponential ax. That's it. Thank you.